Gray Parks, your host today, and it's December the 19th. We have a cold day outside, so it's good to be in the warm studio here. We're going to be talking about a comet that is coming in from outer space, and it's going to leave in a hyperbolic orbit with Richard Schmidt. And Richard, why is this so different? I mean, what's so different about this comet?
Well, what's different is that comets that come from our own solar system, we've seen before, many of them, but not these.
And
these are coming from outer space, from another sun.
They usually have an elliptical orbit too, so we see them time and time again.
A comet that comes from within our solar system does have an elliptical orbit, meaning that we'll travel around the sun, not in a circle, but ellipse, coming far out, but it continues to come around. Coming from outer space, a comet comes through, passes through our system, and goes on its way. And the reason for that is speed. It's coming so fast, it can't be captured by the gravity of the sun.
Oh.
And that's the difference.
Well, tell us about this interstellar comet.
I brought some pictures that, if we can bring them up on the screen. The first one is from the Hubble telescope. We have this Hubble telescope out there in space, and it's looking out there. It's our finest telescope, and we can see this comet that's coming in from another star. And you can see the glow around it, and even a little tail beginning to form. Now that's pretty far out.
Yeah.
And we were just lucky that some guy, an astronomer, not a professional astronomer, but a amateur, built his own telescope. He's looking out there and he sees this little smudge, and it was moving. It was not in the same place every night. And so he says, "Hey, what's this?" And he reports it. And a professional astronomer the next day sees it and confirms it. And so, boy, we got something. This was in October of this year.
Yeah.
And August. It was in August. And so they've been tracking it since August, and they're picking up data on it. And from the data, they're saying this thing is going at 93,000 miles an hour.
And it's already passed through
It has made its closest ascent on the 8th of December.
So it's on the way out.
It's on its way out now, yes. Yeah. And it passed a little beyond Mars, okay?
Well, now, 93,000 miles an hour. How fast is our spaceships that go out to Saturn, or, you know, Cassini, how fast was it at the fastest
around
point?
40,000.
40,000.
Yeah.
So it's very fast, but 100,000 miles an hour is really fast.
Too fast, yeah. I mean, 40,000, we still can go pretty far with it.
Yeah.
And in fact, if you bring up the next illustration, it shows a lot of that's our whole solar system there with the Kuiper belt on the outside. The Kuiper belt is a whole bunch of asteroids that are beyond the orbit of Pluto or Neptune. Neptune's sort of on the edge of the Kuiper belt. Beyond there, there's this cloud, as shown in this illustration, of like
asteroids?
Clumps. Yeah, asteroids, clumps of material that never was included in building the planets within. And those lines that were coming out were the different paths of the spaceships that we've sent out into space to explore. And so that's a beginning of what we're looking at. If you take the next picture, we'll show the path of this new comet that we've seen. It's coming in, it passes outside. That red circle is the Mars orbit. And so just a little bit beyond the Mars orbit. And so it comes in from the right, passes by, and slews out to the left.
Well, now, did it come close to Mars? Mars could have been on the other side of the sun from where the comet passed.
I don't know where Mars is at, at this point. Okay. But that's the orbit of Mars, and it's beyond the orbit of Mars. It would not have struck Mars.
The point is, if Mars had been on that side of the sun, there, it might very well have attracted the, although it's going too fast, I think, to have been attracted.
It would have
with
had some gravitational pull on the, but not enough to alter the trajectory too much.
Well, the sun has had a little effect on it too, hasn't it?
Well, that's why this is bent here. It's bent by the gravitation of the sun.
All right.
And so if you work out the equations, you'll see it'll be hyperbolic.
Right.
And hyperbolic means it's not closing in on itself like an ellipse. Ellipse is a closed path. Hyperbolic is an open path.
Well, the parabolic.
Parabolic is in between.
Well, it's coming in and it's going back out in the same direction. It's coming.
Parabolic, it comes in, goes around the sun, and goes out the other side.
The same direction it came in.
Well, the opposite direction. It's coming in, now it's going out.
Yeah. Okay.
And so parabolic is very, it's the edge.
Okay.
It's the edge between going in a periodic path and going into an open path.
Yeah.
Parabolic is an open path, but it's that edge.
And I assume that we've had some parabolic comets since they bring that up.
I
Or
don't
have we
know.
identified them? I don't know either.
I mean, it's so touchy to get that exact number.
Yeah.
It would be a low probability, but it could happen. Now, we've had a lot of exploration about other suns and trying to find out if they have planets. Well, how do you find a planet around a star? The star is too bright to see the planets. And so they came up with new techniques of seeing how the sun would wobble a little bit because of the gravity of the planet going around it. And that was the first indication that there were planets around stars. But they wanted to find small ones. It takes a big one to wobble the sun enough so that you can see it move. So they came up with this idea, let's see if the brightness of the star dims a little bit as the planet goes by it.
And as I recall,
Well, we're bringing up on the screen right now the technique that they used.
The plane in which the planet is traveling has to be near the equator.
Yes, it has to be
we have
a
to
line
be
of
looking
sight.
at the edge. Yeah.
We look at edgewise, a planet going by the sun as seen on this scheme here. As it goes by, there's a dip in the intensity. And we have this special spacecraft up there. It's a telescope designed just to look for the intensity and look at many stars at the same time, 150,000 stars at once.
Oh boy.
And keep looking for years, 3 or 4 years even, so that you can get some data on tiny things like the Earth. If it's an Earth size going by a sun size, the Earth is about 1/100th the diameter of the sun.
Okay.
Well, 1/100th the diameter, you have to square that when you're talking about the area that's being blocked. That's 1/10,000th of the light disappears. We had to build a telescope that can sense 1/10,000th of a dip. That is pretty sensitive. That's the limit of our capabilities today. And we did it, and we have identified some Earth-size planets
Exoplanets.
Exoplanets around stars that are out there. And so from that, we've got, 4,000 or more identified planets going around stars. So we know it's very common to have a solar system around every star.
But the problem is we just don't have something that's strong enough that we can see those exoplanets in any detail, right?
It's the blindness. You're getting so much light from that star.
Well, that's
it just
true.
blinds
That's
you.
true.
You can't see them.
Yeah, that's true.
And so that's why we had to develop these other techniques. And what they found was that our solar system is not like the most common one that's out there. The most common one out there has planets somewhere between the size of Neptune and Earth. And we don't have such a planet. So we're different from the most common solar systems out there. Sort of a surprising thing. But at any rate, to get back to the how these orbits are, I've got another one. Here it is. These are pictures of the paths that comets would take. If the comet was coming in, it'll be on that outer one. That blue line there is hyperbolic. Parabolic is the green line, and ellipses are in red. So it's all the same kind of a formula. It's just based on how fast something is going. The further out you go from the sun, the slower you can go and still be captured by the sun. If you're going really fast, it means you're going to escape the sun. Yeah. And that's what's going on. If you're going fast enough, like this comet that's coming in from another star system, is going so fast, it scoots by like on this blue line.
Yeah.
And
whereas something like Halley's Comet that comes by every 75 years, then that's on the elliptic.
That's beyond the red ellipse that we have.
Yeah, it takes 75 years, though, for it to go.
Takes a long time, yeah.
Around that. That's a long distance away, too.
That's right.
I don't know what the distance is on that, the major axis of that ellipse. Any idea?
Of the Halley's Comet, I do not know.
Yeah.
No.
It'd be interesting to know that.
No, those numbers are known, just not by me.
Yeah.
Okay.
But the object is that they come back. The one that we're going to talk about at the end is about 2,500 years, the period. So it takes 2,500 years for it to go around that ellipse.
That was one that came from outside our the limit of our solar system. Yeah. It was so far out that it takes that long to go around. 2,500 years is a long time.
Well, we'll see the Oort.
I don't know if it's from Oort or from Kuiper. It could be the external part of Kuiper.
Yeah, you know, okay.
Because Kuiper is pretty big. If we go on to the next illustration, you'll see the path on the left is that sort of a yellowish path. That's the one of this current comet that's coming through our system. The red one is the one that we saw before. That was the first one that came, and that was in 2017. And we didn't see it on the way in. We saw it on the way out, and we didn't get much data on it. It was a very small one, but we were able to compute this pattern. You can see that red line is the computed path of that comet.
And that's called Oumuamua, huh?
Oumuamua. Yes, it's Hawaiian for messenger from outside.
Well, it's the only other interstellar comet that
that
we've
was
been
the
aware
first
of.
one we found. Yeah, that's the first one. We said, gee, I wonder if this is just a fluke or this is more common. Well, so when this new one came in less than 2 years later, they said, wow, this is a great opportunity. It's coming on the inside, and we can take some data. We get their path. We'll be observing this until November of next year. We'll get a lot of data on this. And as the comet puts out this gas, that's that glow that you see around it, that gas has molecules. And we can determine the chemistry of the gas. And from that, we've already found water, or indications of water, and of a molecule that's
cyanogen?
Yeah, that's, I don't want to call it biologic, but it is a biologic component. And so that's exciting to find that, look at that, the comet coming from another star looks a lot like the composition we see in our own comets.
Well, I've read that there's been theories that we have the water on Earth because we were bombarded by a lot of comets with water.
Exactly.
And that's, but you know, that's kind of hard to imagine.
Asteroids and comets have a lot of water. Yeah. And crashing into the Earth as the Earth formed gave us the water that we see now.
You know, that's at least one theory.
I think it's a pretty good theory.
Oh, is that right?
I think it's a pretty good theory.
All right.
Because we are finding consistently there's a lot of water on these bodies that are out there in space.
Yeah.
So it's not unusual to see the water. If we take the next illustration, we'll see our planet system. And you see the tiny planets on the inside. Then you have an asteroid belt. Then you see the big gas planets, Jupiter and Saturn, Uranus and Neptune. And there's Neptune, and then you can see Earth is the tiny one, and you take something halfway in between that, and you don't see that in our solar system. And then we have the Kuiper Belt out here on the right side. That's where a bunch of junk is left over from the solar system in building the solar system. Those things out there, each one, if there's a little jog in the path of it due to some gravitational thing, maybe some other comet comes by from outer space, could jog one of these and cause it to come in and loop around the sun. Well, if it loops around the sun, it'll look like a comet. It'll have a tail and everything, and it will have an elliptical orbit.
Now, is the asteroid belt similar to the Kuiper Belt?
Is the asteroid similar?
The asteroid belt.
I would say the asteroid belt would have more dense objects. You get out to the Kuiper Belt, looser. The gravity hasn't really solidified those as much. At least I'm getting that from reading things, that implication. I haven't seen anyone make that conclusion, but it seems it's sort of like that. So when they come in, the volatile materials that are there can be warmed by the sun and form this comet tail.
Now, if
the asteroid doesn't have that.
If our space ships go through the Kuiper Belt or the asteroid belt, either, they have a lot of probability of hitting objects.
Apparently very small.
Small?
We haven't hit one yet.
I know we haven't. But there are all these asteroids that are orbiting
Isn't
around
that
us.
amazing? Space is so great.
Well, but is the belt thin?
Well, you can see the size of it. They tried to get all the sizes
But we're
similar.
looking at it from above. We're not looking at it from edge on. If we're looking at it edge on, is it a very thin belt? So we really can miss it, or is it thick?
This is
It's
trying
not as-
to depict it as it is.
Yeah, it's not a sphere. It's a belt. It's a
The width of that belt there is trying to stay to scale.
like the rings of Saturn are fairly thin.
Yes.
Is the asteroid belt also fairly
It's
thin?
fairly thin, yes.
So it would be easy to miss it.
Oh, no, not that thin. When I say thin, I mean in gigantic terms, okay?
Okay.
As you're going out, it's wider than the Earth.
Oh, okay.
It's wider than Jupiter, probably.
Well, the width that we're looking down on, but the edge of it.
Yeah, the edge size is probably thicker than Jupiter, and look how big Jupiter is.
Oh, you think so?
Yes.
Boy, that's big then.
What happens when you have this disk forming? It tends to flatten out due to gravity. And so we get this flat disk called our solar system. And so the asteroid belt stays within that flatness, okay?
Okay.
But so does the Jupiter is within that flatness. And so that's why I'm guessing that the asteroid belt is at least as wide as Jupiter.
Oh, that's thick.
At least.
Very thick.
And it's probably quite a few times of Jupiter, okay? But as you're going through, you got all this junk out there so far apart that we just go through every time like there's nothing around. It's amazing.
Yeah, it is.
But it's because look how far it is out from the sun, and you take the diameter of that and you multiply it by pi, and you get a huge distance that all this material is spread out upon.
Yeah.
Just to make it visible to you, they have this denser, I'm sure, than actual.
Oh, sure. Yeah,
Okay,
yeah.
so that's a poor depiction in that sense.
Now, I would assume then also that's from material that was left over from the making of the planets.
Yes.
Yeah.
Some of those
Chunks of-
asteroids that were there came in and smashed into the Earth and built up Earth, okay? Those that didn't smash into the planets ended up out there. Maybe some planets crashed together and split up into pieces, and pieces of that planet could be out there in the
Now, we have
asteroid belt.
landed on an asteroid and on a comet, right? We've had a space.
Let me think. I think
and we've had one deep impact. I think was one that went into the comet.
Yeah, we've done a comet and an asteroid. I think we've done both.
And I think you actually presented a program, a Village in Motion program, when we landed on the asteroid, and it was hard to keep. It was hard to keep the lander.
It bounced.
It didn't
You
want.
got a big
it didn't want
bounce
to stay
because there's
still.
not much gravity.
Yeah.
So when you smash, you want to hit very soft so you don't bounce.
That's right.
And we went down as soft as we could, but we still bounced. Ended up on our side. We got some pictures, but not too much. Yeah, that didn't work out so good. The next picture that came up was a picture of a solar system, how it, in its early stages, would just be this mess of stuff. And it coalesces into planets, asteroids, and the outer part just stays very loose, and that would be the Kuiper belt. If we go to the final picture,
Well, so
we see that Kuiper belt is so tiny. It's down in the center of this Oort cloud. This Oort cloud is like a globe. It's a sphere of particles.
Yeah.
So far out. Look at the size, the different size between that tiny dot in the center being the Kuiper belt around our solar system and this Oort cloud. And we're saying that this comet that came in was probably part of an Oort cloud or a Kuiper belt of some other solar system.
Yeah, so it's
that got
beyond
knocked out of its orbit by something close by, came by, knocked it out, and it's been traveling for years, and finally came into our solar system, and we observed it. And we're looking forward to see some more of these, to get more information about what's going on in space.
Well, you know, I'm sure that they've been happening all the time. We just haven't been able to discover them. Now, it's interesting that it's interesting.
Very hard to see.
It's interesting that Borisov, with his camera, with his telescope, was able to identify. I mean, he happened to be looking at a specific spot in space where this
he was looking at the stars, and he happened to notice a little smudge.
Well, he saw it one night, and the next night he saw it had moved a little bit. Yeah.
Hey, I got
right.
something here. Okay. And then he reported it to a central place where all astronomers look. And then this fellow out in Arizona, I think it was, he saw that. He started checking it out. And he says, by golly, that's a real one.
Yeah. Now, Oumuamua, since we didn't detect it until it was on its way out.
Yeah.
But I mean, we didn't get we were not getting as much information from that. But there must have been hundreds and hundreds of these interstellar comets coming through that we just have not been able to identify. I mean, you don't have two in
Well, if two came
years.
in within 2 years, then you figure it's pretty common.
Yeah.
And we'll expect to see more.
Yeah.
And we're going to keep looking.
And the interesting, I gather that what we know about that comet now shows that it really isn't all that much different from our other comets. Is that
That's
true?
the amazing thing. Now we can imply that other solar systems are very similar to our solar system.
Yeah.
And they're looking at the trajectory of that comet to see if we can project back and find out what star did it come from.
Yeah, and that would be a feat if we
That'd
could
be a great thing if we could do it. Yeah, we're working on it.
Especially if it must have been deflected by other systems. Now, our sun probably is not the only solar part of the solar system that would cause a deflection in its orbit. There must be other systems as it has moved throughout the system.
Doesn't mean that it came near any other system.
It doesn't mean that it did, but the likelihood.
When we trace back, we'll answer
see.
your question.
Right?
Okay. Yeah. Space is so empty.
Yeah.
It's really amazing. And so now this object that's coming probably had a clear shot all the way through. It may have come close to some other large body, and if it did, its path would be altered. But
So that would make our problem of tracing it back to its origin even more difficult. That was my point.
yes, but still, we know what objects are out there. And if we trace back and we see it's coming near some object, we now know how to mathematically trace that one.
Oh, okay.
Yeah, we can do it.
Good.
We're going to try.
Well, Let's go back to the one we just had, the Kuiper Belt and the Oort cloud.
Sure. You want to bring that up?
Well, it's going to take a...
Okay, number 9. They're working on it.
Can't go back to it? Okay, sorry. Well, I just wanted to make sure that people saw the arrow that pointed into the Oort cloud. You mentioned it, but
Yeah. It's right in the center.
Yeah.
See how the
the
that
arrow, yeah, the
magnification
blue arrow.
of that center is what's shown up on the top. And they had to magnify it because you can't see that detail down in the center.
And the system that's up above is the Kuiper Belt, which is outside Neptune.
Right.
And that's all within that
In that
small
little dot in
area
the center, yeah.
in the Oort. Okay, that's what I wanted to...
Fantastic magnification there.
Yeah.
But of course, that's just an artist drawing, but it's depicting everything that we know.
Okay.
All right?
So what else do we know about these comets?
What else can we tell you? Well, the fact that we're looking at the composition of the comets and seeing that it's similar to what we see with our own, we're making that conclusion that the other systems are made very similar to ours. We'll pursue that further. What we're after is there life elsewhere? Is Earth the only place where there's life? We doubt it very much. But we're looking for evidence. And we're trying to find out, do we find molecules out there from other systems that are the same molecules that would be produced by living life?
Well, the fact that the comets, many of the comets have water in part of their makeup would be encouraging, it would seem to me, because all these comets come from breakoffs of other planets or whatever it is, and so therefore the fact that they have water in their tails and the coma would seem to me to be very encouraging, that we have exoplanets that have water on them. And water, of course, is probably essential for our
Yes, those
system.
are the conclusions that we're going to reach. If we find that the comets coming from other stars have composition very similar to ours, then we'll assume, yes, there'll be water. If we keep seeing water on these comets, we'll assume that they've got water on their planets.
Especially if it was the comets that caused our water on Earth. Well, I got one more picture to show you. Let's do the last one. This is called the Hale-Bopp comet, and I don't know if you all remember it, but is that no? Yeah, that's right. That's the Hale.
I know I saw it.
And I saw it for months. I could walk
it
out
was
my
up there
front
a long
door
time.
and look up in the sky, and here is this Hale-Bopp comet. And it's quite a comet. It has a period of about 2,500 years, close to it. It was very large. It was somewhere between 25 and 50 kilometers at the core, whereas most of them are much smaller than that. It had an extremely long tail and a large coma. So I hope everybody here at Green Spring was able to see that back in 97, I think it was, 95 to 90, it was covered in 95, and I think it's 97 is when we saw it for several months. Another thing about the Hale-Bopp comet, we had this group in California, the Heavenly Gate group. There were 39 of them, and who decided that that comet, it was their path to get to heaven. So they all, when they came closest to the sun, when they all took a poison, laid down, and died, so that the spacecraft that's following this comet could come down, pick them up, and take them off to heaven. So you know, there's so many things that people have attributed to comets throughout the whole history. It's kind of
It was
interesting
used
to read
as
about.
an indicator of bad things to come.
Yeah.
Probably was used as a sign of good things to come too.
Possibly, and they blame earthquakes. They blame all
Exactly.
on the
Anything that
comets.
comes at the same time, hey, that's the cause.
All right. Well, folks, that's our discussion on comets today. I hope you enjoyed our talk about the Borisov and the comets in general. I found it very interesting.